Tonight, we welcome Dr Anjali Piette, Assistant Professor at the University of Birmingham in the School of Physics and Astronomy. She grew up in Durham in a multicultural Belgian, French, Indian family and went on to do an undergraduate degree and a PhD at the University of Cambridge, specialising in astrophysics. Following this, Anjali spent 2.5 years as a Carnegie postdoctoral fellow at the Carnegie Institute for Science in Washington, D.C. Her work focuses on exoplanets and their atmospheres, from brown dwarfs to Jupiter-mass planets, mini Neptunes and rocky worlds, using a combination of theory and observation, including the observations from the James Webb Telescope, and this reveals the diversity of these exotic worlds. In 2023, she was selected for the NASA Exoplanet Explorers Program, which brings together students and researchers in the field of the exoplanet study from all around the world. So let's put our hands together and have a nice conference with an Astronomical Society welcome for Anjali.
Hi everyone, thank you so much for the introduction, and it's a great pleasure to be with you all tonight. I'm gonna share my screen. Okay, is that showing up okay?
That's fine, thank you.
Brilliant, awesome. So yeah, as you've already said, I'm Anjali and I research exoplanets and their atmospheres. And I'm going to go into more of what that means and some of our exciting results that have been coming in recently. You already mentioned the James Webb Space Telescope, which was launched just a couple of years ago. And with that, we've had such an influx of data and a lot of new results. So I'm excited to share some of those with you in this talk. But I always like to start off by on more common ground, if you like, starting off with our own planet, the Earth, and the solar system. And as we can see here, our Earth is one of 8 planets orbiting the Sun, our star. And until about 30 years ago, these were the only planets that we knew about. And so they really informed everything that we thought about what planets are like and how they form. So for example, we see that the inner planets in the solar system, Mercury, Venus, the Earth, and Mars, they're all smaller, rockier planets, whereas the outer 4 planets are giant planets. So we have the gas giants, Jupiter and Saturn, and the ice giants, Uranus and Neptune. And so you could be forgiven for thinking, well, surely this will be the same everywhere in the galaxy, right? You have your small rocky planets close to the star, your giant planets further out. That would seem to be the general picture. But actually, it turns out that exoplanets are a lot more diverse than we thought based on our own solar system. And if I click here. So an exoplanet is any planet that orbits a star other than the Sun. And as many of you, I'm sure, see in the night sky, and by the sounds of it, take lots of lovely pictures as well, we can see hundreds, if not thousands, of stars in the night sky. And on average, we think that there are at least 1 exoplanet per star out there in the galaxy. So that means that if you're looking up at the sky and you're seeing thousands of exoplanets, thousands of stars, sorry, you are also technically seeing thousands of exoplanets. Thousands of planets, of which some will definitely not be habitable, but some of them maybe could be. So that's a really exciting prospect. And of course, with the naked eye and from the Earth's surface, we only see a fraction of all of the stars in the galaxy. And so if we consider the 100 billion stars in the Milky Way, that's a lot of exoplanets that are out there. So as I briefly mentioned, exoplanets are very diverse, a lot more diverse than what we see just in the solar system. That includes diversity in size. So this is a really lovely graphic showing artists' impressions of different exoplanets. And the solar system planets are in here as well, just for comparison. So can you see my cursor on the screen as well?
Yes.
Yeah. Fab, great. So down here, I'm just circling Jupiter. And you can see there are quite a few planets, exoplanets in this figure that are a similar size to Jupiter, but there are a lot that are very small. We have lots of small rocky planets dotted around here, and there are quite a few planets that are even bigger than Jupiter, even quite a lot bigger. So there's a real diversity here. And I mentioned that we expect there to be on average, at least 1 exoplanet per star in the sky. We haven't found all of the exoplanets in the galaxy, partly because we're limited by what we can do with our telescopes. Also, the amount of time that we've had, it does take time to observe them and to discover them. And so far, we know about almost 6,000 exoplanets. And every time I give a talk like this, I have to look up the new number because it increases every few days. So it may have gone up since I made this slide. So that's quite a few exoplanets. And in addition to the diversity in size, we also see a lot of diversity in their temperatures, which is really interesting to me as someone who cares about their climates. So we have some exoplanets that are as cold as minus 175 degrees Celsius or colder, and we have some that are really hot, going even hotter than 2000 degrees Celsius. So you can see how, compared to the climate of our Earth, for example, the climates of exoplanets can be way more diverse, and there are lots of interesting processes that happen in these atmospheres at such different temperatures. And so naturally, we can think about the clouds on these planets, the winds, what are the atmospheres made of? This is all a lot more exotic than what we see on Earth and in the solar system, and it's really exciting to study. And so later in this talk, I'm going to be showing you two specific examples. These are two exoplanets that we have observed with the James Webb Space Telescope, which I'll tell you a little bit more about in a moment. And one of these is a giant planet. This is just an artist's impression here on the left. It's a giant planet called WASP 18b. I'll come back to it in a little bit. But it's a giant planet that, unlike the giant planets in our solar system, which are far away from the star, this one is very, very close to its host star, which means that it's being roasted by the star, and that affects its atmosphere and its climate. The second planet that I'll talk about is a type of planet that we don't have in the solar system. It's called a mini Neptune. It's bigger than the Earth, smaller than Neptune. We don't know what these planets are actually made of completely, so they're very mysterious, and it's a topic that I'm particularly interested in. And so this particular mini Neptune is one that we have observed with JWST, and I'll tell you a little bit about what we learned about its atmosphere. But before I dive into that, I know some of you are really keen on exoplanets already and might know some of these things, but just to catch everyone up, I want to talk about how we observe exoplanets and since when. So the very first exoplanet that was discovered around a sun-like star was 51 Pegasi b. So on the left, this is just a comparison of the size of 51 Pegasi b compared to the Earth and Jupiter. It's somewhat similar to Jupiter, but a little bit bigger. And this is a planet that orbits a star called 51 Pegasi, which is in the Pegasus constellation. And unlike Jupiter, this is yet another gas giant that orbits very close to its host star. So compared to Jupiter, which is very cold, 51 Pegasi b is more than 1,000 degrees Celsius in temperature. And this is a planet that was discovered in 1995. So the first exoplanet to be discovered around a sun-like star was discovered less than 30 years ago. And that's kind of interesting because a lot of things that we think about in astronomy were discovered in ancient times or hundreds of years ago. And yet exoplanets are so common, we think, in our galaxy, but it took quite a long time to discover them. It was done within our own lifetimes. So why did it take that long? As you can maybe guess, it's because they're difficult to detect. These, compared to stars and galaxies out there in space, planets are relatively small. And just to give you a sense of scale, if we think about the closest exoplanet that we know of and what it looks like as seen from the Earth, that planet would look about as big as a tennis ball if it was on the moon. And down here, I have a little scale diagram of the Earth and the moon and how far apart they are. As many of you may have seen already, if you look through a really nice telescope and look at the moon, you can make out some nice craters and things going on. But seeing a tennis ball or even a few tennis balls isn't going to be possible, even with a really big telescope. And that's the same with exoplanets. We can't, for the most part, we can't actually image them, the planets themselves. What we see is actually a blob of light, which is the star that the exoplanet is orbiting, and the exoplanet all mixed together in one little pixel in your camera or detector of your telescope. So I just told you it's really, really hard to detect exoplanets, but obviously we do detect them. So how do we do it? Since we're not, for the most part, resolving and seeing the exoplanets separately from the star, we're seeing them all as one pixel of light. And what we can do is to measure the brightness of that little blob of light. And so for planets that pass in front or behind of their stars, what we see is that when the planet is in front of the star, it blocks out some of the light from the star, and it makes the star look dimmer for maybe a couple of hours. So in this diagram, we can see the planet initially is not passing in front of the star, and right now, you know, on the planet on the left, we see light from the whole of the star. So it's this level of brightness. Then as the planet starts to transit in front of the star, it starts to block out light from that star. And so it looks as if the star is dimmer. And then once the planet passes over to the other side of the star and no longer covers it, we go back to the same level of brightness where we see the whole of the star. Now, this is a dip in brightness, which we can detect with telescopes. And as you can imagine, planets will orbit periodically, like the Earth does around the sun. And so every orbit of the planet, it will once again cause this dip in brightness. So the way that we know for sure if an exoplanet is that we look for not just one dip, but ideally quite a few dips to show that the exoplanet's going round and round, and we keep seeing it every time. So this is one of the methods we can use to detect an exoplanet. But as I've mentioned before, I focus specifically on the atmospheres of exoplanets. Now, it's already pretty hard just to do the detecting part, let alone to look at a really specific part, like specifically the atmosphere of an exoplanet. And this is very challenging, but we are able to do it, and even more so with our new James Webb Space Telescope. So there are several methods that we can use to observe the atmospheres of exoplanets. I'm going to focus on one of them, which is a personal favorite and one that I use in my work, but there are other methods as well. So this is called the secondary eclipse method. And I've just talked about when the planet passes in front of the star, but this method actually focuses on when the planet passes behind the star. And the first thing to note here is that, yes, the star is very bright and it's brighter than the planet, but the planet also emits some light. Actually, the Earth emits light. Even we emit a form of light ourselves as people. And we can sort of think about this in a day-to-day context, where if you've ever looked through an infrared camera, you might have spotted that people or your dog or anything that's warm will glow in infrared light. If we go to something that's hotter than people, for example, a piece of very hot metal, it can glow red, hence the term glowing red hot. And if we go to something even hotter, like the flame of a Bunsen burner, then we see a blue glow. And if you remember from chemistry lessons back in the day, when a Bunsen burner has an orange flame, it's hot, but when it has a blue flame, it's even hotter. And so the trend across these three images here is that as you get hotter and hotter, the radiation emitted by the object gets more and more blue, or in technical terms, the wavelength of the light gets shorter and shorter. So when it comes to exoplanets, a lot of them we look at in the infrared because they glow a lot of infrared light. But the hottest exoplanets also emit some visible light as well. And our telescopes are designed such that we can detect this infrared radiation as well as this visible optical radiation as well. So how do we actually go about detecting this glow? Once again, I'm turning back to this diagram of the orbit of the planet around its star. And we're going to focus now on when the star passes, the planet passes behind the star. So just before the planet passes behind the star, we can see the day side of the planet, in this case, this nice mustard color, and we see the star together. So that's two sources of light, planet and the star. Then when the planet is behind the star, it's hidden, so we only see the star. That's a little bit less light. And then when the planet comes back around the other side, once again, we see planet and star, and the brightness goes back up again. So this is similar to how we detect planets. Sorry. But this time, instead of the planet hiding part of the star is hiding the planet. So it's important to note here that many of the exoplanets that we are seeing are a little bit different from the Earth in the sense that on the Earth, the planet spins relatively quickly. So within 1 year, we have a lot of days because the Earth is rotating. But for many of the exoplanets that we're looking at, the same face of the planet is pointing towards the star all the time. So that's similar to the way that the moon shows the same face to us on Earth all the time. And so this means that for a planet, one hemisphere, the dayside hemisphere, is permanently the dayside, and it gets really blasted by radiation from the star. And then you also have a permanent night side, which can get pretty cold. So when we're looking at the planet passing behind the star, we're actually seeing the permanent dayside and seeing, that very relatively hotter environment. So what is it that we actually see? As I just mentioned before the planet passes behind the star, we see this higher level of brightness, starlight plus planet. Then when it's hidden behind the star, we see only the starlight, which is a bit less. And then we go back up to the slightly higher level of brightness with star plus planet. And so what we're looking for is this dip in brightness. It's a smaller dip compared to when the planet passes in front of the star, but it is a dip that we can see. And the size of this dip is something that is important because the brightness of the planet tells us how hot it is. So an object that is hotter will emit more light. And that means that if the planet is very hot, when it passes behind the star, we're hiding a lot of light. We're missing a lot of light that was there before. And so the dip that we observe is a pretty deep dip. But if the planet is cold, then it wasn't emitting that much light to begin with. So when it passes behind the star, it doesn't make as much of a difference. And the dip is relatively smaller. So this already tells us our first hint about the climate of the planet, which is how hot is that permanent dayside of the planet. Now, another thing we can do is that we can look at the size of that dip in brightness, but at different colors. So if you imagine taking a telescope or a camera and putting a colored filter on it, for example, if you put a red filter on your camera and telescope, you would only see red light coming from the star and the exoplanet. So you could say, okay, I'll measure the depth of that dip just with red light. And then you could take a different filter, for example, a blue filter, and do the same thing again and see, well, how deep is that dip just in blue light? And looking in different colors tells us about what the atmosphere is made of. And the reason for that is that there are molecules in the atmosphere of the planet that leave these kind of color fingerprints on the light that is leaving the planet and making its way to our eyes and telescopes. So this planet is emitting a glow, emitting radiation, and as that radiation moves through the atmosphere, it bumps into molecules in the atmosphere, and those molecules will absorb some of that radiation. And the molecules prefer to absorb radiation in particular colors. And the other colors, they'll just let them through. And so that leaves this fingerprint on the radiation that we see in our telescopes. So this is something that it's a method that we use for planets, but it's actually also used for stars as well. And so I wanted to show this example. This is actually a solar spectrum. And of course, if we take a beam of sunlight and pass it through a glass prism, you get a rainbow because the light from the sun is made of many, many different colors, similar to other stars. And usually if you do this with a prism, you just see a nice continuous rainbow. But if you zoom in with some clever sort of instruments to sort of zoom into that rainbow, that's what you see on the right-hand side here. It's a solar spectrum. And And all of a sudden, the rainbow doesn't seem so continuous. We have all these black lines here, which are colors where the light has been taken out. So what's happened here is similar to the cartoon on the previous slide, which is that as the radiation was leaving the sun, it bumped into atoms in that case, so like sodium atoms or hydrogen atoms. And those atoms absorbed some of the light, but only very specific colors. So for example, hydrogen atoms really like this color right here. And so we've got a really big gap there. Sodium atoms really like these two colors here. So that leaves these two gaps there. And we also have gaps from iron and other atoms as well. This is a nice illustration of how different atoms in this case, but also molecules, kind of eat away at different colors of light from the light that comes through the star or through the planet's atmosphere. So the same basically happens with exoplanet atmospheres, where if we have, for example, different, light of different colors all traveling through the atmosphere together, then in this cartoon example, the red light gets all the way through, as does the orange and the green and the blue. But this molecule right here, it doesn't care about the other colors, but it does like to absorb the yellow light. And that means that the yellow light doesn't get through. And our absorber here on the right sees the red light, it sees the orange and the green and the blue, but it doesn't see the yellow. And so we, as observers, can use that information. We can say, okay, I saw all the colors apart from yellow. Based on that, I can infer that there's a molecule in that atmosphere that likes to absorb yellow light. And if we want to know which molecule that is, we can actually use experiments on the Earth to figure that out. So we can take actual gases. We can take a box of water vapor or carbon dioxide, pass some light through it, and figure out which colors of light that gas, those molecules like to absorb. And we can kind of match it up with the fingerprints that we see from stars and exoplanets and figure out, okay, which molecule actually is it that would absorb this yellow light? And oh, look, I just detected it. So I'm going to show you some real data sets where we see those missing colors based on the molecules in an exoplanet's atmosphere. But those data sets I'm going to show you are taken by the James Webb Space Telescope. So I wanted to introduce that telescope first. This is a photo that I like to show. This is actually a scale replica of JWST, which is the acronym for the James Webb Space Telescope. And it's nice because you can see how huge it is compared to all these people at the front. The mirror is 6.5 meters wide. And this is the biggest space telescope that has ever been launched. It's a really fun toy to play with. We can detect a lot of really cool things with it. So that's been really exciting. Okay, so going back to these two cases that I sort of introduced before, I'm going to start off by talking about this giant planet, which is being roasted by its star because it's orbiting really, really close to the star. So this is a planet called WASP-18b. It's not a particularly inspiring name, but it's named after the survey that discovered it. And WASP-18b is a relatively similar size to Jupiter, just a little bit larger. But what's the really big difference is that WASP-18b has a permanent dayside at about 2,700 degrees Celsius. So pretty hot, especially when you compare it to our own Jupiter, which is around minus 110 degrees Celsius. That's a pretty big change, and it really affects the climate in this planet. So I'm going to show a couple of slides here just illustrating the observations that we made of WASP-18b using JWST. So this is just going to outline how we see the planet gradually going behind the star. And on the right, this is the actual brightness levels that we measured with JWST. This isn't just a cartoon, this is the real data. So initially, we could see the permanent dayside of this planet next to a star. So we see the maximum brightness, which is the data points just here. Next, the planet started to pass behind the star. So we only see a little bit of the planet. And that brightness that we're observing is going gradually downwards. Then when the planet is completely behind the star, we see only the star, not the planet, and we reach the minimum brightness. And this is the brightness that we see across all the colors that we looked at, all combined together. So just to go over that again, we see this dip in brightness. Now, we did also measure this dip in brightness separately for a whole range of different colors. So let's see what that looks like. Here, the y-axis on this figure is showing that relative brightness, so effectively the size of that dip that I was just showing before. But for every point along here, it's showing the size of that dip for a different color. Now, these colors aren't the visible colors that we see in the rainbow. They're actually infrared light. So beyond the red end of the rainbow. Yeah, this is the colors that we're using to observe exoplanets because that's where they appear the brightest. So here we can see that the brightness of the planet is relatively high here at the bluer end of the color scale. Gets a little bit dimmer and then brighter again. There's a bit of a bump, and then dimmer again, and then brighter again, and then dimmer again, and then brighter again. So these bumps aren't just an accident. These are real data points, and they're actually telling us something. We happen to know that these bumps are the fingerprint that water molecules leave in an atmosphere. So the fact that we can see not only this bump, but also this bump and this bump is telling us that there is water vapor in the atmosphere of WASP 18b. Now, it's not the sort of balmy temperatures and steam that you would get in a sauna or something like that. It's very, very hot, but it is nevertheless water molecules in this atmosphere. So that was a really exciting discovery because we had actually looked at this planet with other telescopes in the past that weren't as big as JWST, and we couldn't actually make out these water bumps. The spectrum or the data looked a lot flatter, but because JWST is so big and so sensitive, it was able to pick out these water fingerprints, if you like, and that was a first for this planet. So just zooming in a little bit on this fingerprint and these bumps that are caused by the water molecules, the size of these bumps is really useful again. And what it tells us is how much water vapor is there in the atmosphere. So the more water vapor we have, the bigger these bumps would be. And when we sort of analyze this data and compared it to different models we have for the atmosphere, we found that these bumps are actually not that big, which explains also why we couldn't see them with older telescopes. And these are actually pretty small water bumps, which tells us that there isn't that much water vapor in this atmosphere. It's present, but there's just not that much of it. And that's really interesting because this atmosphere is so hot. So what is happening here is that, yes, there are water molecules in the atmosphere of WASP 18b, but a lot of the water molecules are being torn apart by the heat of the atmosphere. And so some of the molecules stay intact as H2O, but a lot of them get split up into individual oxygen and hydrogen atoms. And that means that it's reducing the amount of actual water molecules that we can detect. And it's the first time that our data has been sensitive to this kind of process happening in an exoplanet atmosphere. So it was really exciting to see that we could tell that this is happening in that atmosphere. So another thing that we were able to get out of this data set for WASP 18b is a bit of a temperature map, if you like, of the dayside. So because we've just seen the planet passing behind the star, we were really just probing the dayside of the planet for the most part. So we don't have any information about the night side, but we do have an idea of the temperature map, if you like, just on the day side. So that's what this temperature map is showing on the left. And this is sort of a longitude, latitude map, like you get maps of the Earth. And this sort of orange spot in the middle is the middle of the day side, so the point of the planet that's closest to the star. And it's the reddish orange color is showing the hottest temperatures, and as it gets more purple around the edges, it's getting colder. And so what the data is telling us is that this planet is really hot right in the middle of the day side, and then quite quickly it gets colder sort of radially outwards. And that's interesting because it's a little bit different to what we expected. So a lot of planets that are kind of similar to WASP-18b, but maybe slightly cooler, they often have very strong winds that sort of go east-west horizontally around the planet, sort of around the equator. And these are winds that are generated because the day side is really hot, because it's a permanent day side, and the night side is really cold. So all that energy flows through these really strong jets and winds that travel to the night side. And these winds are so strong that they change the temperature structure of the day side. So here we call this hottest point in the middle, we call it the hotspot, not a particularly imaginative name. So if you have a really strong wind going eastward, for example, that hotspot will actually shift a little bit eastward, and you'll see it not right in the middle of the day side, but a little bit offset. But here we're seeing the hotspot right in the middle of the day side. And what that's telling us is that the winds are actually a bit different on this planet. What we think is that the winds are actually going radially outwards, including sort of north-south winds, carrying energy from that middle really hot part over the poles to the night side. And we've sort of pondered about why those winds are going in that direction and not going sort of east-west. And one theory is that there could be magnetic fields inside this planet that add drag to the wind, and they sort of stop the wind from going east-west, and instead they make it easier for the wind to go north and south. And so in this artist's impression on the right, these sort of kind of vertical lines are portraying this sort of more north-south type of wind compared to what we've seen on some of these other hot giant exoplanets. This was a really interesting thing to see in the data as well. Okay, so now I'm going to move on to the second case that I'll talk about. And this is a mini Neptune. It's called GJ1214b, and it's a planet that we know to be very cloudy and hazy. So just to introduce this planet, this is just a cartoon of it, artist's impression here. The planet is called GJ1214b, again, a bit of a weird name, as many exoplanets are. And GJ1214b is what we call a mini Neptune, which means that it's bigger than the Earth, but it's smaller than Neptune. The reason this is really interesting is that there are no planets in the solar system that are in this size range. In the solar system, the rocky planets is either the Earth or smaller than the Earth, and the giant planets are either Neptune or bigger than Neptune. There's nothing in between these two. But when we look at the exoplanet population, the most common size of exoplanet is actually a mini Neptune in between the Earth and Neptune. So that's an interesting philosophical question, because if that's the most common type of exoplanet, how come we don't have one in our own solar system? We still don't know the answer to that question. But it does mean that we're really motivated to try and understand what mini Neptunes really are and what they're made of, because that is still a mystery right now. So we know how big mini Neptunes are. We've measured their sizes. We've even measured how heavy they are. But there are lots of different possibilities for what they could be made of on the inside. So one option is that mini Neptunes could be like giant versions of the Earth, so kind of a rocky core to the planet, and then surrounded by an atmosphere made of hydrogen molecules. So that would be quite a puffy atmosphere around that rocky center. But another option is that you could have what we call a water world scenario. So this is a planet that has so much water in it that there are really thick oceans, but they cover the entire planet. So not like the Earth, where you would have some land sticking out, but really deep oceans around the whole planet. And so, and on top of that water, you could also have, again, an atmosphere made of hydrogen molecules, for example. So both of these scenarios kind of sound like they come out of science fiction. We haven't seen this kind of planet before, but these are genuinely some of the best options that we have for these mini Neptunes. And what we want to know now is, how do we tell the difference between these different scenarios? How can we tell what the middle of the planet is made of? And one of the ways we can start to get at that is to measure what the atmosphere is made of. Our telescopes can't dig into the center of the planet, but they can tell us information about which molecules are present on the outside in the upper atmosphere. So So that's what we've been trying to do. And so going back to GJ1214b, this is a planet which, again, had been observed with older telescopes before the James Webb Space Telescope. And with that data, we had found out that this planet is enshrouded in clouds and hazes. So clouds, similar to on Earth, are particles in the atmosphere which have condensed from the gas to the liquid or solid. So we can have liquid water clouds or solid ice cloud particles, or we can have clouds made of other molecules as well. And hazes are similar to clouds, but they form in a slightly different way. And so hazes can be thought of as sort of like the smog that you get in cities. Sometimes they're these little particles that can form through different chemical reactions in the atmosphere, and they behave a little bit like cloud particles. So we know that GJ1214b is really enshrouded in these clouds and hazes, and that had actually made it quite difficult to figure out what its atmosphere was made of, because the clouds and hazes were blocking our view of the atmosphere. But then along came JWST, and we were able to make a new kind of measurement for this planet. So before, I was talking about just observing the planet when it passes behind the star, but we did something a bit extra for GJ1214b. This is a method that has been used for other planets as well, but it's even better with JWST because it's so sensitive and can look at really interesting colors of light in the infrared. So what we did was to observe GJ1214b throughout its entire orbit. And like I was showing before, this is a planet that has a permanent day side and a permanent night side. So as it went round its orbit, we saw the day side, then the edge side, then the night side, the other side, and then basically saw all the way around the planet. So that gives us a lot of information, and it's really useful to figure out what's going on in this atmosphere. It's a type of observation which, if we could do it for every exoplanet, I think we would, but it's quite expensive to do because you have to observe for a really long time for the whole orbit. So for many exoplanets, it's not possible, but it was possible for this one. So because we could see all the way around this planet, it meant that we could make a temperature map of all the way around. And so we have this information about how temperature changes with longitude. And again, you can see this hot spot like we did on the hot Jupiter. This planet is actually a lot colder than the WSP-18b that I was showing before. It's around 500 Kelvin on the day side, but actually that is colder than we expected it to be. So we can see really well how hot this planet is because we can see the light that it's emitting all the way around, including the night side. And so we know for sure that it's really colder than we expected. And the only way to explain that is that some of the light from the host star is not making it into the atmosphere. So what's happening is that because GJ1214b is so cloudy and hazy, those clouds and hazes are actually very reflective, and about half of the light that's coming in from the star is bouncing straight back out. It's being reflected by the clouds and hazes. And that keeps the planet kind of cold because it has this shiny appearance, if you like, because of the clouds and hazes. So for reference, the Earth reflects about 30% of the light from the sun because of clouds and the ice caps and things like that. And here we think it's around 50% that is being reflected. That's telling us something interesting about the properties of the clouds and hazes on this planet. We know that they're very reflective and very abundant, and we can actually try to learn more about their properties. Now, this is another data set similar to the one I was showing for the giant planet, where the data points are showing the size of that dip, the relative brightness of the planet as a function of different colors as we go along here. And so once again, we can see that the brightness of the planet looks really different in different colors. So it's a bit fainter around here and brighter around here. Now, this dip around here is very distinctive of absorption from water molecules. And so once again, this is one of those color fingerprints due to water. And it means that we have tentatively detected water vapor in this atmosphere, which is really exciting. It's the first time we got some chemical information about this planet. Now, you may have noticed I just said a tentative detection of water vapor. The reason we're not 100% sure about this one is because this dip right here is caused by water molecules, but methane molecules also have a fingerprint that's kind of similar and does something similar at these colors. So it looks pretty much like water vapor, but it's possible that there's also some methane mixed up in there. And with the other data set I showed you, there were multiple bumps. So we could be really sure that it was the water. Here, because of the way we had to set up the observation, we're only sensitive to this one bump. So there's a bit of uncertainty about whether it's definitely water, if there's also some methane. But either way, it's the first time we've got some kind of chemical information about this atmosphere. So going back to what are mini Neptunes made of, this hasn't solved the question completely. It's going to take a lot more than that, but we are able to measure the atmospheric compositions of planets like GJ1214b. It's not the only one where we can do it. And so what we're doing is to build up a sample of observations for all these different types of atmospheres. And JWST is observing dozens of exoplanet atmospheres of all sizes and temperatures. So we can build up this picture of what's really going on for the mini Neptunes, but also for the giant planets and rocky planets as well. And so overall, with all of this data, what we're able to do is to piece together what's going on with all of these different exoplanets, why they're so different, how do they form, and how do they look different to our own solar system. And it's by understanding the differences to what we have in our solar system that we can get some context for why our planet is the way that it is and why we don't have mini Neptunes, for example. What are those differences? And so there are many open questions still. There's a lot of exciting stuff happening, but this is only the beginning. So watch this space. New discoveries keep on happening, and we'll keep learning more and more about exoplanets. So I'm going to stop there. Thank you so much for listening, and hopefully we have plenty of time for some questions and discussion.
Anjali, thank you for a fascinating talk. Could I ask you to stop sharing your screen, please? And then we can go back and see all the people who are attending. Those people online, as usual, can you give me a digital hand so I can bring you into the discussion? And people in the room, can you attract my attention, usually with a waving hand, or a £10 note will do. I don't really mind. So we're open for questions. Have we got any in the room? Tony Morris in the room.
Hi, Anjali, that's really interesting. Can you tell the age of a planet by the rate of desiccation of the atmosphere?
That's a good question. So the ages of planets are usually determined based on the age of the star that they're orbiting. In terms of the level of desiccation, there are many different things that can affect how much water you have in the atmosphere. So it wouldn't necessarily tell you the age, but there are ways to measure the age of the star. And so since the planet, a planet will form a little bit after the star formed, but kind of at a similar time. So if we know the age of the star, that gives us a good estimate of the age of the planet. There are some stars and planets where we know the age relatively well, and others where we don't know it well at all. So it really depends on the system. But that's the way that we usually measure planet age.
Okay, Tony. Okay, thanks. Looking out for any other questions. You mentioned it being expensive to observe a total orbit of a planet. So how many observations do you actually get your hands on before you say, right, this is proper data, this isn't just a one-off?
So do you mean how much we can ask for effectively?
Yes.
Yeah, so what happens is, so JWST is obviously used for exoplanet atmospheres, but also many other areas of astronomy. Actually, when it started to be designed, it wasn't designed for exoplanets. It was designed to observe very, very, very distant galaxies, to study cosmology and things like that. Because exoplanets are so recent, that was added as an extra science case later on. And so we share JWST with all our colleagues across astronomy. And what happens is we put in proposals. So once a year, there's a call for proposals. And if you have a planet or a galaxy that you want to observe, you write a proposal explaining what it is you want to observe and why it's important. And then all of those proposals go in, they get read by review panels and get graded, and the top proposals get chosen. And that the time that JWST has to observe is filled by these sort of top choices of proposals. It's very competitive because, as you can imagine, a lot of people want to use the telescope. We in exoplanets often have pretty collaborative efforts where we group together and put in several proposals. And so even if not all of them get accepted, some of them do, and we have data to work with. And yeah, we actually had a deadline for the latest call for proposals in mid-October. So just before that deadline, everyone is working hard to finish their proposal and make it as good as possible. So we'll find out, I think, next March what's been accepted for this cycle.
Okay, so are there any other data sets that you actually use?
So I personally focus mostly on JWST data, but there are lots of telescopes that are used for different things. So my colleagues in Birmingham use a whole range of telescopes on the ground to actually detect the planets. So that includes telescopes in the Canary Islands, in Chile, in France, in Antarctica even. I have a colleague who went to Antarctica recently, which is really cool, literally. And so they use those telescopes to discover new exoplanets. There are also other telescopes in space, for example, the Hubble Space Telescope. That's one where it has been used for exoplanet atmospheres as well. So yeah, lots of data sets coming in.
Okay. Peter Lloyd, online.
Yes, hello, Anjali. Thank you very much. A most interesting talk. Mine's a slightly technical question. I'm intrigued as to how you get so much data from JWST. On the one hand, I can't believe you need one observation per wavelength, but can it take the whole spectrum for you in one go?
Yeah, that's a really good question. So in both of the examples that I showed, all those wavelengths were observed in one go. So we use a spectrograph basically to get that all in one go. It does depend on the modes that you're using, though, with JWST. There are lots of different modes that look at different colors, different wavelengths. And if you want to use two different modes, then you'll have to go back and do it twice. So with each of the data sets that I showed, they each use one instrument. There are actually two different instruments for the two different planets. If I wanted to observe both of those color ranges that I showed, but for the same planet, I would have to observe it twice, one with the first instrument and then again with the second instrument.
So it does measure the spectrum, but it only shows a bit of the spectrum out of one instrument and another bit out of another instrument. Have I got that right?
Yeah. So the data sets that I showed in any one plot, that was a single instrument in one go. But you can piece them multiple together to get an even wider range in one go. So some instruments actually look at a pretty wide range on their own. Some of them focus on a slightly narrower range, and you might want to put a couple of them together to complete your data set. It really depends on the science case and the question you're trying to answer. And in some cases, the instruments that look at a narrower range of wavelengths, one of the reasons for that is that they can look at that range of wavelengths at higher resolution, so they can split up the different colors more, which can give us different information. So, for example, the data that I showed for the giant planet was at higher resolution than for the mini Neptune, and also had a bit of a wider coverage in terms of the different water features, and that helped us to detect that water more confidently. So different instruments have different pluses and minuses depending on what you're trying to do.
Yes, actually, I think that answers what was going to be my follow-up. But presumably, the resolution of the spectrum you get does depend on whether you're using a narrow one or a wide one. Yes, so because presumably you would like very high resolution, wouldn't you? But you don't get it.
Yeah, so actually that's something that's done from the ground because, you know, if you want a really high resolution spectrum, you need a really big spectrograph, and it's very difficult to send that into space. But that's something that, yeah, that's done from the ground, where you can have such a big spectrograph. And so the ELT, the Extremely Large Telescope, another imaginative name from astronomy, that is being built at the moment. So that will have a very high resolution spectrograph. And there are other telescopes that already exist on the ground, including in Chile, for example. And so people use those to look at exoplanet atmospheres as well.
they can.
But I didn't have time to mention, but you can actually look at those lines that you can see, you know, the missing colors that you can see as the planet orbits around the star. There's a Doppler shift in those lines, and so you see them move side to side throughout the orbit. Obviously, to see that, you need the very high spectral resolution to see the lines, and so that is something that is done from the ground.
I see. Okay, so thank you very much.
Thank you, Peter. Gary in the room.
Thank you, Anjali. Thinking about that, you've got the ability to measure the temperature of a planet, and you can detect water vapor or moisture water. Is there any that you're finding that maybe hit the sweet spot for sustaining life as we know it?
Really good question. Yeah, we're looking for it. And so basically especially, well, actually with most techniques that you can look at exoplanet atmospheres, the colder you go, the more challenging it is. So that's partly because the planet emits less light, and also a colder atmosphere will be a bit more compact, and it's harder to see through it. But it is something that we're able to do in some cases. So if we think about a planet like the Earth, or a small rocky planet with a relatively thin atmosphere, that's very challenging to observe, and we're actually looking for the presence of atmospheres around rocky exoplanets. Those planets where we're looking for those atmospheres are not quite the same as the Earth, because the Earth is pretty far away from the sun, and we're not able to even detect a planet that's exactly like the sun orbiting a star, exactly like the Earth orbiting a star exactly like the sun. So there are other rocky planets which are orbiting smaller stars, for example, but closer in. And for those ones, we're still looking for definite evidence of an atmosphere at all, let alone what it's made of. But there are other planets which are a bit bigger, also mini Neptunes, a bit like GJ1214b, but a bit colder. Those ones, we can get measurements about what's in the atmosphere and the composition of the atmosphere. And the reason we can do that is because they're big enough. So they're not rocky planets like the Earth, they're a bit different, but it allows us to look at the atmosphere because they have these bigger atmospheres. And also there are some that are cold enough that we think they're in the habitable zone of their host star. But then it raises a whole load of questions of if it's technically the right temperature, that it could maybe be habitable. And if we see maybe some water, does it actually mean that it's habitable? Does it mean that there's life? It's a very complicated question, because it takes more than just water and just the right temperatures to have life. You need to have the right nutrients. You need to make sure that there's a surface there that the life can live on, and that the history of the planet is such that life could have developed. So it is probably one of the biggest and most motivating questions in exoplanet science, but it's made up of a lot of other little questions, like what are the surfaces like on those planets? You know, is it a water world scenario? Is it a rocky planet? That will make a difference about whether it's habitable. And what are the signatures that we would expect from life? So we're all working away at the different pieces of the puzzle to one day hopefully be able to detect life, but it'll take a while, I think.
Thank you.
Okay. Roy in the room.
Yeah, I mean, one of the things that was occurring to me was, how far away from a star are we now detecting planets? I mean, for example, if we were trying to look at Saturn from here, going around another star, I mean, that'd be once every 23 years that you would get the dip. So we've not really been observing that long. So presumably all we're measuring at the moment is planets close in. And are we able to sort of do eventually out to sort of Jupiter, Saturn regions of these stellar systems?
Yeah, so you're absolutely right that we are very much biased towards detecting planets that are close to their host stars. And that's why they're the first ones that we've discovered. And the further you go out, there are several challenges. One, as you mentioned, is that you have to wait for a long time for it to come back around. So if you want to detect more than one transit, you have to wait a while. But there are other aspects as well. So there are a couple of different methods to detect the planets. The one that I mentioned, where the planet passes in front of the star, that is very sensitive to the angle of the system. So you can imagine if the system was face on, you would see the star and the planet would move around it in a circle on the sky. You would never see the transit because it would never appear to cover the star. So you need it to be exactly the right angle so that the planet passes in front of the star. Now, the further away the planet is from the star, the harder it is to get that condition right. And so we're less likely to see the transit. There is another way to detect planets where it doesn't have to transit, and that is the radial velocity method. So you rely on seeing shifts. So those lines that I showed in the solar spectrum, they will move left and right as a planet orbits around the star, and it's due to a Doppler shift. And so you can detect that Doppler shift in the lines and infer that a planet is causing the star to wobble. But to detect that wobble, you need to account for a lot of other effects. So stars aren't these perfectly homogeneous spheres. They have activity. So when you see an image of the sun, you see like sunspots and flares and things like that. They get in the way of the signal of the planet. So that currently is a challenge in detecting planets like the Earth and planets that are far away from the star. So right now, an alien, if they had the same technologies we do, they wouldn't be able to detect the planets in our solar system. We're only sensitive to planets that are much closer in. But eventually, as the technology gets better, we'll move to further and further out planets.
Okay, great.
Is there any problem with an area of overlap whereby you're not sure if you're looking at a multiple star system or an exoplanets, or are the two fields completely separate?
Sorry, I didn't quite catch the question. Can you say that?
Area where is there a grey area where you can be unsure whether you're observing a multiple star system or an exoplanet?
Yes, that is a common thing that is tested for, especially if the binary system is just a grazing binary. Obviously, if the binaries fully eclipse each other, then the drop, you wouldn't have a planet as big as a star. So then it's kind of well, it depends on the type of star actually, but you can sort of tell that it's a star. But if it's a grazing, if it doesn't fully cover the star but just a part of it, that can look a bit like a planet. So there are tests to see if that's the case. You can tell based on the shape of the dip, also by looking with different telescopes, by checking it at several different things. So to confirm that a planet is really a planet, usually you have to use different methods to detect it, to prove that it's the size of the planet and the mass of the planet. And that's how you definitely confirm it.
Thank you. Okay. I'm not seeing any more questions. Oh, I am seeing another question. Back to Tony.
When you took out hot Jupiters with very close orbits to the host star, how long can those types of planets stay in that configuration before they're evaporated away, so to speak?
So actually, even before they completely evaporate away, another option is that they could spiral in and fall into the star. So I don't actually remember the number off the top of my head. It'll depend very much on the configuration of the system, but it is possible that these planets aren't stable forever and that they will spiral inwards. On the topic of the atmosphere being blown off by the star, that is a process that's really important, actually for the mini Neptunes. So I showed the case of GJ1214b, but there are lots of planets that are mini Neptunes. There are also lots of planets that are what we call super Earths. So they're bigger than the Earth, but they're smaller than the mini Neptunes. And these are two distinct populations where we see a lot of mini Neptunes, a lot of super Earths, but nothing really in between. And so what we think is happening is that these planets are born with these quite large atmospheres made of hydrogen. But the mini Neptunes, they tend to be a bit colder. They're a bit further away from the star, so their atmosphere is protected. But the super Earths, they're actually a bit closer to their host stars. And so they receive more radiation. That radiation blows off the atmosphere, and you're left with a smaller, sort of rockier planet. So yeah, the escape of the atmosphere is a very important process, actually, and we're seeing that really sculpt the exoplanet population.
Okay, Tony, thank you. And back to Peter Lloyd.
Oh, thank you, Paul. Yeah, I hope I could just slip in before you close the question. I just wanted, if I may, to take up a point you made earlier in your talk. You said you believe there was, on average, 1 exoplanet per star. Well, if you take our system, we've got 8 planets. Does that imply that you believe that only 1 star in 8 has a planetary system?
So based on the statistics of what we detected so far, some stars don't have any detected exoplanets where we've looked, and some have multiple systems. We see a single planet, we see systems with 7 planets. So based on what we're seeing, it's possible that, yeah, some stars maybe don't have exoplanets, or they have planets that we're not able to detect yet.
Well, that's in a way what I was hoping.
Yeah. So as I mentioned before, the solar system planets, we wouldn't be able to detect around another star. We're not sensitive to that yet. So, you know, these numbers could increase.
So a system like our planetary system, not too far away, you wouldn't be able to detect anything.
If the star is the same as the sun and the planet's the same, yeah, we're not sensitive to that right now.
Oh, well, I'm actually quite relieved, because if you think about the way planetary systems form, you feel that probably every star has one, and I like to think that one does.
They might.
Well, thank you very much.
Okay, Peter. I think it's also how you're actually measuring your average, mean, mode, median. But there you are. Okay, ladies and gents, I'm not seeing any more questions. Have a quick look around. Will you join me in giving Anjali Piette a huge Max Winston Astronomical Society? Thank you. Thank you very much.
Thanks for having me and for the great questions.